Okay, so I'm just going to do a quick little, hopefully, overview over this polarity and dipole, and then go a little bit further in depth over the hybridization that I was talking about in class today. Hopefully this helps. Okay, so with polarity we have um, this idea of, we hear these words polarity, and then we hear the word dipole. Okay, and dipole is talking about the molecule, and polarity is talking about a bond. Okay, and that's my best way to differentiate between those two. Sometimes they're used incorrectly or interchangeably, but I think in most chemistry classes this is something that would kind of clear up anything. So you can have water be a polar molecule. This means that the bonds are polar between them. So if we have water out here, okay, um, this bond from here to here is in fact going to be polar. Okay, oxygen is going to be stealing the electrons for most of the time, versus hydrogen that's hardly getting any. So he becomes more positive because he does not have the electron, and this negative, partially negative, is because he's stealing most of the electrons most of the time, and electrons are negative. Okay, so that should make sense. Now, water also has a dipole because the entire molecule is polar. So you have the positive end being down here, and you just draw a plus sign, and the electrons are moving upward. And this is referred to as the dipole, where these two refer to polarity. Okay, so your molecules that are going to have a dipole are bent molecules, trigonal, planar, pyramidal, excuse me. And everything else is going to be symmetrical, meaning that when you draw a methane, okay, which we're going to be talking about a lot on the next slide, this is its electron dot structure, its Lewis structure. I know I didn't draw it with dimension, but this is what it really looks like as far as electrons are concerned before they start pushing each other in that Vesper theory. And so here it is literally symmetrical both ways, where water, when you split it up, is not symmetrical. And so this is going to have a dipole, where this one is going to be a non-polar molecule. Okay? And of course, we can calculate the polarity of a bond by subtracting their electronegativities. Okay? So you could get oxygen's electronegativity subtracted from hydrogen, and you would know exactly how polar these bonds are. So I hope that kind of clears up anything that you were wondering about with the polarity versus the dipole. All right, so let's go to a little bit more difficult of a topic, in my opinion, the hybridization. So today we had a bell ringer that was methane, CH4. Okay, and so this is methane. Okay, and methane is how it's named in organic chemistry. Okay, and in organic chemistry, endings and all of these names tell us a lot. Of course, we're not going to get too far into that today, but okay, so you have CH4. First, you need to identify the central atom. Okay, so carbon is our central atom, and so you're going to write the electron configuration of carbon, which is 1s2, 2s2. I'm going to go ahead and erase that, otherwise it's going to be in our way later. Okay, 2s2. And then we have 2p2. Okay, so in bonding, remember that valence electrons are the only thing that's really being involved. So we want to be with the outer, remember valence electrons definition is electrons in the outermost shell. And so remember these numbers right here at the front, these are the shells that it is. So this might say S and P, but really the entire shell is a second shell. So the valence electrons of the second shell are these right here. So it has 4 valence electrons, which should match up to your group number because it's in group 4. Okay. So now what we need to do is we need to look at this as if we were drawing it on an off-bar diagram. Okay, and then we'd have the 2p. And remember, these are px, Py, and Pz. So now I'm digging into a couple chapters ago, these Aufbau diagrams and things. So if we put a little energy to this, this could be heat, this could be stirring, whatever, that we actually lift all of the valence shells onto the same orbital level, okay, same energy level. Sorry about that. Whoa, now we're going back. Okay, and so what that does when you put energy to it, now all the valence electrons are in the outermost shell, and if we were to fill these in, we'd have 2 on this one, and we'd have 2 on the next one. Now, if you remember, the Pauli exclusion principle said that each suborbital would fill before the next orbital. Each one would have 1 before any one suborbital would have 2. So now that these are on the same energy level, this electron here actually is displaced and will be moved over here. Okay, so really what this now looks like is we have 2s with 1 electron, and then 2p, px has 1, py has 1, and pz has 1. Okay, and so now this is literally, we have 1s, and we have 1, 2, 3 orbitals of p. So this is an sp3 hybridization, okay? And this makes sense because if we were to draw this molecule out, we have 1, 2, 3, 4 places for things to connect, okay? So now hydrogen comes in and has 4 hydrogen, each volunteering an electron to go ahead and bond. Okay, and literally what this means is this s, it's an sp orbital, means that it's partially an s orbital and partially p. And this 3 means that it is 75% of a p shape and 25% of an s shape. Okay, so it's still going to have a little bit of a p, and I know in class today I drew it as 2 big p orbitals, and when I went back and looked at my organic chem book, it all kind of came back to me. And so that's why I wanted to make a video tonight. So literally it's going to, we'd have our little 1s, you know, small guy right here. And then we would have 1 on our x, so it would have like a little bit of the p and a big side of the p, okay? And then we would have the same sort of thing on the top here, and then the same sort of thing that would be y. Then we'd have the same sort of thing on the z-axis, okay? And then this S1 usually drops back, so it would be our other side of the z-axis. And this really is what gives us the VSEPR theory. So these orbitals here, or hybridization or molecular orbitals, okay, this is a molecular orbital, okay, this is what gives us this valence shell electron pair repulsion, okay, and this is what gives us the shape. So literally it ends up looking like a tripod, okay. All right, and all of these sp3 orbitals, sp3 is always going to be what we call a sigma bond. And a sigma bond literally is just a single bond. Okay? All right. And then these are kind of cool because we can actually do one, like if I did water here. Okay? And of course, we know what water looks like. When we did the same thing, central atom, we would have 2s2, I'm going to skip a little bit here, and a 2p4. So now we'd have, if we put the energy into it, okay, we have our x and our y and our z, pz, py, pz. And so now this one would be filled, and then we'd have 1, 2, 3, 4. Okay, So now this one doesn't have to move over. It doesn't have to be displaced because there's one in everything. So that's fine. But now, as you can see, these two are full. And these two are the only locations where a bond can form for these H's. So these right here, these already filled, end up being these lone pairs that you see in oxygen. So when we do hybrid orbitals, these lone pairs and these sigma bonds, we can see that these are evident, and you can tell where they are. Okay, and then I had like a little picture here, but we'll get back to that. Okay, now pi orbitals or pi bonds. Pi means like this, so a sigma bond is going to be that single bond, and that's going to be sp3. Okay, and a pi bond is going to be a double bond. Okay, and these get a little bit more confusing as far as the hybridization goes. But I'm going to try to just give you a quick look at it here. Okay, so pi bond is a double bond, and double bonds are going to be sp2. Okay, and then I can show you kind of how that works. Down here. So if we have our Aufbau diagram, okay, and let's say that we have a double bonded carbon. So this is our molecule of ethene. By the way, ethene, E-N-E, always means a double bond. And that A-N-E, it's a single bond. That's a little bit of organic chemistry. But so this bond right here, so we have two central atoms now. And so this gets a little bit more confusing, and when we increase the energy level, it's not quite as simple as it was with that sp3 where we can draw it out and see it. In fact, what happens is we get 3 sp2 orbitals and 1 2p orbital. And I'll kind of show you what that means. So what we have is 3 sp2 orbitals, which, so we have carbon and carbon. We have sp2 1 2 3 1 2 3 on each side, so we kind of get this little one, and then we get one like this and one like this. Okay, so those are our sp2s, and this again, remember sp2, that would be now 66% a p orbital and 33% s orbital. Okay, and we do this for both sides. Okay, with a little overlap there, that's our sigma bond. Okay, and when it bonds with hydrogen, these are all going to be sigma bonds. Okay, and so this is our little carbon there, and another one, and another one. And if hydrogen came in, these were all these sigma bonds. Okay, and now we have a sigma bond in the middle. This is this bond right here. So I've drawn these sigma bonds here. And now we have this last one, and that actually is the 2p. And 2p means that there's no s orbital about it. It's actually 2p orbitals, or a p orbital. Okay, and so what this is a p orbital that comes from carbon on both sides, and it overlaps. And now these two can't move independently of each other. So this whole molecule turns as one big molecule because of this double bond. And that's what that last one. And so this right here, the overlapping of two p orbitals, that is a pi bond. So a double bond is actually made up of one sigma bond and one pi bond. Okay. And then a triple bond is even more confusing, which we're not going to go into it, but as long as you know that sp, an sp hybridization is one sigma bond, I don't know why I'm writing this out, and two pi bonds. Okay, so it's going to be a little bit more confusing. It's 2 sigma and two pi bonds, which is always going to be a triple bond. Okay, so when you see something